Bueno, Ramón, ya estamos.
Gracias. Okay, so welcome everybody to the IFIMAC+ICMM joint seminar series on Congress Matter. It is my great pleasure to present our fourth speaker of the series today, Andrés Castellanos, who is going to talk about Straintronics with 2D materials. For those of you who don't know Andrés, let me say a few words. Andrés is a Tenured-Scientist at ICMM, the Material Science Institute in Madrid of the Spanish National Research Council, CSIC, since 2017. And previous to this position, he was at IMDEA Nanoscience, also here on campus. He was a tenured researcher for 2 years, and before that, he was a postdoc at TU Delft in the Netherlands, working with Herre Zant for 4 years. And, you know, despite being very young, Andrés is a very well-known expert in van der Waals, heterostructures, and 2D materials in general. And specifically, he explores novel 2D materials, studies their mechanical, electrical, and optical properties, with a special interest on applications of these materials in nanomechanics and optoelectronics. And, you know, part of this work has been considered as pioneering in the field of 2D materials beyond graphene. And, you know, he has reported some of the earlier works on novel 2D materials like molybdenum disulfide, black phosphorus, titanium trisulfide, franckeite, etc. And among his achievements, his works on strain engineering on 2D semiconductors and on photodetectors based on 2D materials are considered like seminal works in the field by the community. His research is funded these days by an ERC starting grant, which started in 2018, and his paper has been cited more than 15,000 times, according to Google Scholar, with an H index above 54 or so. And, you know, just to mention another distinctions and awards, he's a fellow of the International Association of Advanced Materials. He has been included in the highly cited researchers of Clarivate Web of Science in 2018, 2019, and 2020, so for 3 years in a row. He was selected as one of the top 10 Spanish talents in 2017 by the MIT Technology Reviews. And he also received the Young Researcher Award for Experimental Physics of the Royal Physical Spanish Society in 2016, which is a very prestigious prize here in Spain. And finally, let me mention that Andrés got his PhD here on campus from Autonomous University in 2011 in working with Nicolas the Great. So he's a very successful example of this young generation of scientists that we are training here at Canto Blanco campus, and of the collaboration at synergy that we aim and try to promote between different institutions here in this campus. And this series of seminars is an example of this synergy we are trying to improve. And before giving the floor to Andrés, let me inform you about a couple of details about these seminars and the talks in general. All of you know probably that weekly announcements that you received include a YouTube link to the previous seminar, the recorded seminar of the previous week. So this seminar is also being recorded. And the second thing is that you can make questions during the talk and also at the end of the talk, and you just can write them in the chat, or you can raise your hand. And your microphone will be muted during the talk, but you are welcome and encouraged to ask questions viva voce at the end of the talk. And as I said, just write them in the chat, and I will allow you to ask the questions at the end of the talk. With this, I finish, and again, thank you for coming to this seminar. And Andrés, the stage is yours.
Thank you, Ramon. Thank you for the introduction, and also for the invitation. I feel really honored and a little bit intimidated by the quality of the previous speakers' seminars. Okay, so here we go. So can you confirm that you see the screen and the pointer?
Yes, everything okay. Go ahead.
Okay. So as Ramon said, I'm going to talk about Straintronics with two-dimensional materials today. And also, as pointed out by Ramon, I joined the Material Science Institute in 2017. Before that, I was also working in the campus in IMDEA Nanoscience, and I did the thesis in the Autonomous University. So basically, I passed through most of the institutions in campus. In the Material Science Institute, I'm part of the 2D Foundry research group. That is basically a cluster of different PIs with a common interest in two-dimensional materials. All right, and within the two-dimensional the 2D Foundry, I lead the two-dimensional materials and devices lab. That is basically composed now by our postdoc Tsinghua Zhao, that just graduated, our project manager Begoña, and the PhD students Felix, Hao, Wenliang, and Sergio. These are basically the real heroes here, because in April 2017, our labs were like this, basically, just a brand new lab and everything to be built up, even like the electrical connections, everything, okay? And just a little bit more than 1 year later, so the labs are now with state-of-the-art equipment, fully equipped to work on two-dimensional materials. And now we have all the facilities from the fabrication of isolation of two-dimensional materials, characterization, fabrication of devices, and measurement. So really, all these guys, they have been working like really hard. All right, but now, before starting with the general topic, I mean, the Straintronics in two-dimensional materials, let's try to introduce a little bit two-dimensional materials. We had previous speakers working on two-dimensional materials in the last 3 webinars of this series of webinars. So I'm not going to go through all the details, but I would like to give just a glimpse of what two-dimensional materials are, and more importantly, to motivate why two-dimensional materials are suitable for Straintronics. Okay, so when we talk about two-dimensional materials, we refer to basically is a way of speaking. So we refer basically to a family of layered materials that they have. For instance, I mean, in this family, we have graphite, we have also molybdenite, we have talc, we have mica, right? So we all know familiar with these materials. So for instance, we have here a small piece of muscovite mica, okay, who doesn't have one of these big crystals of mica at home, right? And all these materials, they have many different applications, right? So because they're actually very different. So we have graphite in the pencil leads, we have molybdenite used as a solid lubricant in engines, talc in baby powder, and mica is traditionally used a lot in pigments in the for instance, the cosmetics. But what makes all these family of materials be alike is the fact that they have strong bonds in plane and weak van der Waals forces out of plane. Okay, so in the case of graphite, for instance, we have these strong carbon-carbon covalent bonds in plane and forms these layers, okay? And between the layers, we have just weak van der Waals forces. Okay, so we have a huge anisotropy in the strength of the bonds between the in-plane direction and the out-of-plane direction. And that makes our life easier if we want to isolate thin layers, because then we can easily cleave these crystals, okay, just using, for instance, a Scotch tape. So basically the process that we use to isolate two-dimensional materials by the so-called Scotch tape exfoliation method is placing a single crystal in a piece of tape. This blue tape is a specialized tape, but you can also use normal Scotch tape. And then basically by folding and peeling, we can cleave the crystal. Okay. I find that this explanation here in a PowerPoint with pictures is always messy, so I brought myself a piece of muscovite. Sorry, we have the piece of muscovite, but this is actually not really good for demonstration because muscovite is quite transparent. So I brought also a little piece of molybdenite. Molybdenite is a semiconducting two-dimensional material I'm going to talk today about. Okay, this, you see, that is quite shiny, and And as I said, so all these layers, they are held together by van der Waals forces, that they can be broken, these bonds between the planes, just by using Scotch tape. So now we have, sorry, with the line in. Okay, so now we have the Scotch tape adhered to the surface. I rub a little bit with my finger, so this very scientific procedure here, okay, in order to remove the air pockets. And now I peel, and you can see how I got thin layers of this molybdenite. All right, good. But now, in order to convince you a little bit more, I'm going to take a blank Scotch tape, and I'm going to put it together. Okay, so this is more difficult to do in life than what you will expect. Okay, so I do this scientific method of rubbing with my fingers. Okay, so at home you can do it like that, but in the lab we do it properly. Okay, and now look what I'm going to do. I'm going to peel off slowly, and you will see how the crystal clips half and half. Okay, so basically we have thinned down our crystals, but just using Scotch tape. Okay, so now we have half the crystal here, half the crystal there. If I take another piece of tape and I do the following, the same. Okay, so I take another piece of blank tape, I attach my crystal of molybdenite here that just cleaved, and I repeat the process. Oh, sorry. I cleaved again the crystal in two pieces. Okay, so I'm repeating this process over and over. I'm thinning down my crystals. Okay, so you can think that eventually you will get a single layer if you repeat this process. Okay. Oh, sorry. I've lost the slide I was. There we are. Okay, so let's continue. So now you believe that with the Scotch tape you can cleave these crystals and you can thin them down. The next thing that we do in order to transfer these crystals that they are they're living on the surface of the Scotch tape or the adhesive tape, in order to transfer them to a substrate, what we do is we place just as our acceptor substrate in contact with the tape, and we peel off gently, and what you get is the transfer flakes on the surface of your acceptor substrate, like this one here. Now, the problem with mechanical exfoliation is that you cannot control the position of the flakes that you transfer. You cannot control the thickness of the flakes that you transfer. So you need a technique in order to basically scan quickly the surface of your substrate and find the two-dimensional crystals you want to work with. And optical microscopy is a quite common method used to basically quickly scan through the surface of the two-dimensional of the substrate and finding the two-dimensional material flakes. Okay, so in this corner here, if we zoom in, you will get this image here. So this is this corner here, and you can see how we have different flakes. This is a transmission mode optical microscopy image. So black means very opaque, and you can see how you have flakes that they are very opaque and flakes that they are more and more and even more transparent because they are thin and thin and thinner. And eventually there are flakes like this one here that is just one single layer. Okay, so this is a single layer of molybdenum disulfide transfer on polythymethylsiloxane. Okay, and we can find it just with the optical microscope. All right, and now let's go beyond. Okay, let's go farther with the motivation part of the talk. Okay, so why we want to use two-dimensional materials in devices like Straintronic devices. Okay, and I have to start with the Moore's law. Okay, so we all know that electronics is evolving towards scaling down more and more the transistors. So we all hear in the news that the Intel is now going beyond 7 nanometers. AMD is already in 7 nanometers node, and they keep scaling down more and more the transistors in order to put more transistors in the chip. You can see this is the number of transistors on a chip, and this is the year of manufacturing. And you can see how we are following this semi-empirical law that it was at the beginning. It was Gordon Moore, the one coined this Moore's law in order to predict the trend of this scaling down in the semiconductor industry. Okay, so we are reaching this point here where we are already in the industry in the 7 nanometers. AMD is now going to the 5 nanometers node. We are reaching very, very close to the fundamental physical limits of electronics. Okay, and then semiconductor industry, of course, has some strategies in order to deal with this and continuing scaling down, or at least continuing the, let's say, improving of the electronics. And the first strategy is what is called more. Okay, it's basically continuing doing what they are doing with silicon with other materials, basically. And that is, I mean, also some people, they call it beyond CMOS, but more is cooler for the talks. Okay, and let's try to understand how these two-dimensional materials fit in this strategy of beyond CMOS. Okay, so this is a cartoon of a typical field effect transistor. Okay, so we have a semiconductor channel that is contacted between drain and source electrodes. We have a dielectric on top of it and a gate electrode. And just by changing the voltage we apply to the gate voltage, to the gate electrode here, sorry, we can basically generate an electric field that shift the conduction and valence band, you know, and then basically when the Fermi level touches the conduction band, we start having conduction through the semiconductor channel. When the Fermi level lays in between the conduction and the valence band, we are in the off state of the semiconductor material, and therefore the channel is switched off. Okay, and you can see that in this cartoon here, where we have the off state, and then when we apply positive gate voltage, we start having conduction at this point here. Okay, and this is because we are shifting the Fermi level or shifting the bands depending on your reference point. Okay, okay, that's okay. What happens when we start scaling down and down and down our semiconductor channel? What happens is that at some point, when the length of the semiconductor channel is smaller than a threshold value, then this electric field that we generate with the gate is no longer a parallel field, electric field. It has fringing effects, okay? Therefore, it is not so efficient in switching off the semiconductor channel. And then you start having what is called the short channel issues. Okay, these short channel issues is nothing else but that you're trying to switch off the semiconductor channel and you still have some current, okay? And you'll see, well, I mean, it's not a big deal. So we have just a little bit of current. So we still have several orders of magnitude between the on and the off state. So we can still do logic operations. That is not the problem. The real problem is overheating. Remember that we have more and more transistors in a smaller and smaller space. So heat management is a nightmare in semiconductor industry nowadays. And if we have, you know, a non-negligible amount of current, even in the off state, electronics is going to burn. Okay, so all the microprocessors in all the electronics, if we don't reduce this off current, they're not going to work just because of overheating. Okay, and where these two-dimensional materials enters into this equation of this beyond CMOS is this threshold length is proportional to the square root of the thickness of the channel. Therefore, you want to have a channel with a semiconductor material that is as thin as possible. And there is nothing thinner than a single layer two-dimensional semiconductor material. Therefore, you can push the limits of electronics just a little bit more than with silicon if we move to two-dimensional materials. And that will happen eventually. I mean, I'm not saying molybdenum disulfide is going to replace silicon in 2 years from now. But at some point, there will be nothing else but two-dimensional semiconducting materials because they will be eventually the ultimate thin semiconductor channels. Okay, but there is also something else that we are reaching also, remember, these fundamental limits. And so not just the pure electrostatics, but there is also the problem with the tunneling. Okay, So in silicon, when we will reach the 5 nanometers semiconductor channel length, we will start having small problems with tunneling. So even with 5 nanometers, we will have a non-negligible tunneling current. And this happens because basically we have to think that when the channel length is long enough, we can think of electrons as classical particles, and they find an electrostatic barrier that you generate with the gate, and then they bounce basically, and they don't pass through. But when we reach to the point of 5 nanometers channel length, this barrier that we are applying with this electrostatic gate, it will be narrow enough to allow a non-negligible tunnel current through it. How this two-dimensional material helps a little bit with the picture? Well, first thing is that as they are thinner, the electrostatics is better, and therefore the barriers, they're sharper, okay? They're more abrupt. And also the dielectric constant of these two-dimensional materials is higher than typical semiconducting materials like silicon or gallium arsenide. And therefore, basically you reduce the probability of tunnel. So it's already calculated that you can push these limits of tunneling all the way down to 3 nanometers already. So we can gain 2 nanometers from 5 nanometers of silicon to molybdenum disulfide, for instance. All right, but there is other strategies to. Oh, sorry, I forgot this slide. So to have a little bit of context already, I mean, this is not science fiction. So already there are a lot of research grade transistors fabricated with two-dimensional materials like molybdenum disulfide, and these research grade transistors, they already have performances that they are quite competitive. I mean, if we compare them with the state-of-the-art microelectronic transistors, that they are fully optimized. Okay, so I mean, these transistors from research, for instance, in this case from Andrés group in Lausanne, these transistors, they are homemade. I mean, just students, go to the lab, do all this mechanical exfoliation I have shown you with the tape. You can imagine this is far from being optimized, and still performances, they're quite good. Okay, so this is very promising. But let's go to an alternative approach to try to solve this problem with the scaling down. And a different approach is what is called more than Moore. Okay, more than Moore strategy, basically what it does is says, let's forget for a second about the scaling down. Okay, so we have enough transistors already. So forget about it, about making them smaller. Let's try to add some functionality to the transistor. So nowadays, basically, transistors are just, let's say, okay, oversimplistically, just a switch, an electrical switch, on, off, basically, right? Let's try to add more functionalities to every piece of electronics. Okay, and that is what the more than Moore approach does. And for instance, with these two-dimensional materials, we have a whole zoo of new electronics that can be exploited. So for instance, we have so depending on the degree of freedom that we exploit, we can have spintronics, valleytronics, piezotronics, etc., etc. And in particular, today I'm going to talk about Straintronics. Okay, that is probably the less explored new electronics from this chart. Now let's focus on what is Straintronics. And basically, Straintronics refers to basically exploiting strain engineering methods to fabricate devices with new functionalities. So we can think of it as using external strain as a tuning knob in order to change the output characteristics of your device. The same way that you use an electric field in a field effect transistor to change the output characteristics, in a Straintronic device, you can use a mechanical deformation in order to change the output characteristics, like in this artistic representation that I have shown you here. As I said, Straintronics exploits strain engineering. So what is strain engineering? It's a general strategy that has been used in material science and also, of course, in semiconductor industry to modify the fundamental properties of a material, but just by changing, for instance, applying a mechanical deformation. And the classical way of applying a mechanical deformation in semiconductor industry and also in material science is by forcing epitaxial growth of materials with different lattice parameter. So in this example here, I've shown you, I showed you a material with a given lattice parameter, and we are going to force the epitaxial growth of this material and this material on top, taking into account that this material has a smaller lattice parameter and this material has a larger lattice parameter. When we force the epitaxial growth of all these materials on top of each other, what happens is that basically we are applying a compressive strain to this material 2, and we are applying a tensile strain to material 3. But this approach to apply strain is not tunable. So once you force this epitaxial growth, you cannot change it. And so, I mean, it's static, right? So if you're thinking about exploiting strain engineering to fabricate a functional device, you want something that you can change in time, right? So, and also, this approach usually yields rather small strains because these three-dimensional materials are typically brittle, okay, and usually it's homogeneous on all the wafer scale. On the other hand, when we think about two-dimensional materials, you can do, I mean, because of the aspect ratio, okay, so they're so large and thin, so you can do many ways of applying strain. So it's almost like a piece of paper. So you can bend it, you can apply directly tensile stress, you can try to pierce them with a sharp tip, like in this case here, where we have a tip of an AFM making an indentation in a freely suspended drum. So you can apply strain in many different ways. And what is importantly, you can change it in time. Okay, so you can, for instance, in this example here with an AFM tip, you can do a central indentation and you can change the amount of strain you're applying with the tip. Okay, can be non-uniform, can be uniform. And from indentation experiments in, for instance, in this case, in molybdenum disulfide, indentation experiments, they have seen that basically these materials, they can stand quite large deformations, around 10%, which is very close to the fundamental limit where the breakdown occurs because the bonds, they break. I mean, the force between the force is so large that the bonds, they tend to break instead of coalescing the effects and starting cracking, okay? Good. So I think these are unique features of two-dimensional materials. So basically this large mechanical resilience is quite outstanding of two-dimensional materials, and maybe here we have a niche application. So that's why I truly believe two-dimensional materials are particularly suited for strain engineering, and therefore it is very interesting to apply them in Straintronics because you can apply quite large deformations. So one will expect a quite large tunability of the output characteristics. But so far, if you take a look to the literature, most of the works, they are quasi-static. So you apply strain, you make a measurement, which usually is quite long. Maybe you change a little bit more the strain, you do another measurement, but you don't use it in order to, let's say, modify something real time. And moreover, most of the studies, they're just fundamental. So most of the studies that you can find in the literature, they're more dealing with strain engineering and not straintronics. So basically what most of the works do is they apply a given mechanical deformation to the layer, and they use some kind of technique in order to monitor the changes in the electrical, optical properties or band structure or something like that, but they don't use it as a device, okay? So the only early examples that you can find in the literature about straintronic devices are, for instance, in Andrés' in Lausanne group, they have this working where they fabricated this freely suspended layer of molybdenum disulfide, and it's contacted between drain and source electrode, and they use the tip of an AFM in order to make an indentation on the freely suspended part, and they could measure how the resistance of this channel changes upon indentation. Okay, so basically they are fabricating a pressure-sensitive resistor, basically. Is one of the earliest examples of a straintronic device, but in my group, we are quite interested in optoelectronics. And this kind of approach is kind of cumbersome. To start with, because you need a working AFM in order to operate your device. And nobody wants to have an expensive AFM in order to operate a device. So you want something simpler. And on the other hand, also, if you just think about research, you say, okay, we can use an AFM, no problem with that. The other problem is that if you have a AFM tip on top of your device, it's difficult to integrate this with an illumination source in order to fabricate your optoelectronic device. Okay. There are other examples in literature, like Schoenberger's group, where they were fabricating basically a fully encapsulated graphene device, kind of exploiting the same technique they use in Schoenberger's group for molecular electronics. They have these mechanically controllable break junctions, and I think they borrowed many of the strategies and techniques that they have there, to fabricate these devices. But so far, they've been focused just on fundamental magnetotransport experiments, so not adding any functionality to the graphene device so far. And also in Stanford's group, they're nowadays integrating freely suspended graphene layers on microelectronic, on MEMS devices, on microelectronic mechanical system devices. But I think so far they have not succeeded on making electrical contacts to the flakes. They just reported Raman spectroscopy experiments on these freely suspended layers upon mechanical deformation. So still fundamental. So at this point, we were wondering what could we add to this field of Straintronics. And in my group, we are relatively successful on finding easy ways, easy techniques in order to solve quite complicated technical problems. And we found out a way of having a good geometry to apply dynamic strain on devices that they are operating on inoperando devices. And basically what we thought of is that we could exploit the thermal expansion of polymers. Okay, this example here are a series of pictures, optical pictures, of a polydimethyl siloxane substrate in where we have made these holes in order to guide your eye. And then we change the temperature of the substrate, and you can see how the substrate basically, when you heat up the substrate, it expands. Okay, so and it's a substantial expansion. You can see it here, right? Okay, so then the idea that we have is maybe we can exploit this thermal expansion of the polymer in order to apply some strain to our two-dimensional materials, right? And we have been developing this technique already for the last 3 years. And one of the take-home messages here is that the technique works quite well, but you have to be very careful with the substrate that you use. Because, for instance, polydimethyl siloxane has a huge thermal expansion, but the young modulus is very small, very low young modulus. It's quite floppy material, okay? And the amount of strain that you can transfer from this polymer substrate to your flake depends on the substrate young modulus. So you need to find a substrate with a large young modulus and a large thermal expansion. And basically, I can tell you that polypropylene or polycarbonate, they're quite suitable materials, but polydimethyl siloxane is a really bad material for this application. Okay, and let's take a look how this looks. Okay, so what we can do with this thermal expansion of a polymer substrate. So in this case here, we have polypropylene substrate, and we have transferred a molybdenum disulfide flake. We have here a single layer and a bilayer. And the way we are going to monitor if we are transferring strain to our material, and if we are able of changing the band structure of our material with the strain, is making micro-reflectance spectroscopy measurements. In the reflectance spectra of this molybdenum disulfide, you have these peaks here. Okay, so you have these peaks, and they correspond to different exciton resonances. Okay, so the A peak here basically corresponds to the direct bandgap transition that you have in the K point from the valence band to the conduction band. Okay, and that gives this resonance here in the reflectance spectra. So this is giving us already a direct information about the bandgap. Okay, this A peak. We have also this B peak, and it corresponds to this other transition because the valence band of molybdenum disulfide is split because of a spin-orbit interaction. Okay, and interestingly, in the multi-layers, we also have this little hump here. This what is labeled IL is interlayer exciton is basically another transition of this nature, in where the electron and hole, they live in different layers. So that is why it's labeled interlayer exciton. Okay, and we can therefore monitor the changes in the band structure of our material just by taking a look to this differential reflectance spectra as a function of the strain, as a function of the temperature of the substrate. So now we can change the temperature of the substrate, you see here, and we can monitor the energies of these peaks. And we can see how indeed, so these peaks, they shift upon heating. So here in this axis here, we have the corresponding biaxial strain. Okay, so this is the temperature of the substrate, and we can correlate with biaxial strain knowing the thermal expansion of the substrate. And we can see how indeed we are able of basically closing little by little the band gap. So we are reducing the band gap as a function of the biaxial strain that we apply to our crystal. And what is important is that now this technique allows us to quite easily change this strain in time. For instance, in this case here, we took a heater and we sent the heater sine wave signal. Okay, and we have here the temperature of our heater changing in time. And we have here the energy of the A interlayer and B excitons in time, following the same, the same signal that we have from the heater. So basically, we can modulate the band structure of our material in time. Okay, so this is already an interesting path, to fabricate a device that works with this strain. But this was a fundamental study, not a device. Okay, so now we are interested in implementing this in an in-operando device, and that was basically the main work of our PhD student Patricia Gant, that recently graduated. And what she did, it was transferring single layer molybdenum disulfide flakes between gold electrodes that were pre-patterned on polycarbonate, okay, in order to fabricate a photodetector, as the simplest photodetector possible. It's a photoresistor or a photoconductive device, basically, in where the illumination changes the conductivity of the semiconducting channel. Okay, so this is what we did, and making it on polycarbonate allowed us to use this trick of the thermal expansion to apply strain. How we transfer these molybdenum disulfide flakes between bridging these two electrodes is by exploiting a deterministic transfer method that we developed in my group, that basically uses a polydimethylsiloxane stamp. We use gel film in order to transfer flakes in the position we want. In this example here, our student, well, now postdoc, so recently graduated as well, Tsinghua Zhao, transferred an indium selenide flake bridging these two gold electrodes on a silicon oxide substrate. Okay, you can see here how we are able of transferring these flakes right at the position we want. Okay, so you can see here the outcome. Good. So then basically the measurement is the following. So we have these two electrodes. We have the molybdenum disulfide channel. We apply a bias between the electrodes, and we measure a current. And upon illumination, we might generate photocurrent. So we will have an excess of current. And that was what we monitor in our measurement. And by changing the temperature of the substrate with the temperature stage, we can change the amount of strain we apply to our material. Okay, and now we have also Tsinghua got new results on indium selenide that has even larger strain tunability. Good. So what we do is we do with this measurement I told you. So we measured the photocurrent that we are generating, or responsivity, that is basically proportional to the photocurrent, for different illumination wavelengths. Okay, so we illuminate our device with different energies. And when we are below the band gap, we generate photocurrent. And when we are beyond, above the band gap, then we are not able of generating photocurrent. Okay, so sorry, if we talk about wavelength, not energy. So what we see in our spectra is that these spectra, they have these two peaks here, okay, which corresponds again to these two excitonic features. And we can change, so what we see here is so these numbers here are the strain that we are applying, plus 0.5% tension to minus 0.8% compression. And we can achieve these strain values by changing the temperature of the substrate. We can go all the way from minus 200 degrees, liquid nitrogen, in where we have minus 1.5% compression, all the way to 110 degrees is our maximum. That is basically you get plus 0.5% tension. So we are limited by the melting of the polycarbonate, actually. And first thing that we see is that these peaks, they shift upon straining, similarly to what we have seen in our previous slides on the microreflectance spectroscopy. So basically, when we apply tension, we are reducing the band gap. When we apply compression, we are actually increasing the band gap. Okay, so you see how these peaks, indeed, they shift monotonically as a function of the strain. Then this is already telling us that we are indeed inducing a spectral shift in our photodetector, which is what we wanted to see. We wanted to apply a mechanical deformation in order to change the output characteristics of our devices. Okay, this is already interesting, but from a practical point of view, if you're thinking about a photodetector, this is the interesting part of the spectrum, because in this tail here is where you have the cutoff wavelength. So basically the maximum wavelength your photodetector can detect. Okay, so we have to analyze carefully the maximum wavelength we can detect in this region here. And what we have seen is that this cutoff wavelength shifts by a lot. Okay, so we are talking here about like 260 milli-electron volts from minus 1.5% to plus 0.5%. So this is a lot. I mean, we are shifting the spectral sensitivity, the spectral window of our photodetector by a lot just by changing the strain. Okay. At this point, you will be also wondering about like this enhancement that we have seen here. So this is already something that we don't have an explanation for the microscopic model that what's going on there. So we know that we have a change in the photocurrent generation mechanism. So when we apply compression to our device, our devices operate in the photoconductive effect, generating photocurrent with the photoconductive effect. And when we apply compression, our devices, they start to have a photogating effect. So we have photogain, but we don't understand yet the microscopics of what's going on to change this mechanism of photocurrent generation. And at this point, you will be wondering, okay, so in all these measurements, you have to change the temperature. So what is the role of the temperature in the actual physics that you're observing, in the actual results? In order to disentangle the effect of biaxial strain and the effect of temperature, we have fabricated sets of devices. One set of devices is fabricated on polycarbonate, in where you have a large thermal expansion. So you have change in temperature and change in biaxial strain at the same time. And we have this other set of devices fabricated on silicon oxide. And silicon oxide has a negligible thermal expansion. So in these kind of devices, you only have the effect of temperature. You don't have the effect of the biaxial strain. And we fabricate this set of devices and we subject these devices to the same temperature cycling. In this example here, I show you an example of a polycarbonate device and a silicon oxide device. And we ramp the temperature from 25 degrees to 100 degrees in both of them. And you can see how in the polycarbonate device, the change in energy of this A exciton is much larger than on silicon oxide. And also the enhancement of the photocurrent is much higher in the case of the polycarbonate device. So basically, the effect of thermal expansion, the effect of the temperature change in all these features that we have observed is very small. It's almost negligible. So the only real effect that we have seen here on the silicon oxide devices is that our features, they broaden up. Okay, so that is the only real feature that we have observed that is attributed to the temperature. And there is a small, not negligible, but small change in the position of the A excitons. Now we can exploit the fact that we have this strain tunable photodetector And as is actuated with the temperature, so we can again make, for instance, square cycles to our heater in order to change the strain in our device in real time. In this case, is what we are doing. So we are basically changing in a square way the temperature in our heater, and we can therefore change from plus 0.48% to 0.16, 0.48, 0.16, etc., etc. And we can see how indeed we are modulating the photocurrent flowing through our device just by this changing in the strain in real time. If we just zoom in one of these cycles, we see that the time response of our devices is around 20 seconds. Okay, so since the moment we turn on the heater until it reaches the stabilization, so it takes around 20 seconds, which might look a lot, but if we take into account that we are trying to mimic adaptable photodetectors, and one of the most common adaptable photodetector that we have around is the human eye. Human eye takes around 10 minutes to accommodate to different lighting conditions. And in our case, our device will be able of adapting in just 20 seconds, okay? But still, 20 seconds might be a lot for a lot of applications, okay? So actually, this is the home of this part, no? So this is almost, I'm almost finishing actually. Basically, so far, what I've shown is just a proof of concept. Okay, so we are just playing with these strain tunable photodetectors, but we know that there are a lot of things to be improved because there are a lot of technical problems that have to be solved. And one of the things, for instance, that we have seen already is that these devices are rather slow. Okay, our devices, they take 20 seconds to change from one strain state to another strain state. And this is actually limited by the heater that we are using. So it's the thermalization time of our heater. And also, even though it's not real, there is no such a large temperature crosstalk, one doesn't want to apply different temperatures to a device in order to operate. So one prefers something that is, let's say, piezoelectric or motorized or something like that. So applying strain through temperature is not so elegant for the real life application point of view. Okay, so we have to think about solving these problems, and we spend quite some time in the group in order to work on these little problems one by one and trying to get all the pieces of this big puzzle in order to, at some point, eventually, we'll be able to put all these pieces together. One of the parts is the speed. Okay, and for the speed, we thought, okay, so if the heater, there is a macroscopic heater, takes a lot of time to thermalize, what if we make a microscopic heater and we place our flakes in the middle of this microscopic heater? So in theory, if the heater is smaller, it will heat up a smaller portion of the substrate and it might be faster. And indeed, we have seen that indeed, using these microscopic heaters, we can reach much faster switching speed. So we are now switching around 10 hertz, so basically 0.1 second. So we increased the speed time by a factor of 100, 200, all right? And also, regarding the need of applying a temperature in order to apply the biaxial strain, so we were wondering, because applying biaxial strain is kind of cumbersome. So because you have to apply strain in exactly the same way in all directions, okay? So it's difficult. Doing it with a thermal expansion is a very simple way of achieving biaxial strain, but doing it mechanically is complicated. So we were working, recently we have some unpublished results using a technique that has been developed already in mechanics quite some time ago, to apply biaxial strain to macroscopic materials in order to apply this biaxial strain to two-dimensional materials. Excuse me. Basically, the technique uses a bending scheme in where we use a central indenter and a substrate that it has a cruciform shape. Okay, so it has a cross shape, and we place our flakes right in the middle. And using this approach, you can indeed change the amount of strain you're applying to the material, and you can get nice strain tunable features And this is important because biaxial strain is a way more efficient way of tuning the band structure of two-dimensional materials than uniaxial strain. Okay, so having a method that allows you to apply biaxial strain in a controlled way is quite useful for straintronics and strain engineering applications. And with this, I already finished. So I hope that I could convince you that strain can be used to add new functionalities to devices, and in particular in our group we're interested in optoelectronic devices. So I hope that I convince you that applying strain to a photodetector can be useful in order to change the spectral bandwidth of this photodetector and also to change the responsivity. And also I would like to transmit you during this talk that little has been done so far on this field. Okay, so as you can see in my talk, there are a lot of technical problems and also a lot of interesting physics that are underlying these problems that are still to be basically work on. So I mean, almost nobody has done anything on this topic so far. And yeah, so with that, I would like to acknowledge the funding sources and acknowledging you for your attention. Although I think today this picture will be more suitable. Thank you.
Thank you very much, Andrés, for this fantastic talk. So please, if you have questions, you can raise your hand or write them in the chat. There is already one question. I can actually unmute you. Let me try to unmute you. And you can ask the question yourself. Let me try to find you.
Hello, this is hello.
Hello.
Andrews, this is one of the nice presentation. I have few questions. As we are working in uniaxial strain to the 2D material, that is MOS2, only MOS2. What makes, in the end of your talk, you mentioned that biaxial strain is superior than uniaxial strain in bandgap tuning. May I know what it makes that? Our line of thought is in commercial or in how I can say that in real time applications like wearing flexible electronics, we will have more uniaxial strain rather than biaxial strain. So we thought that we can go on crack in the uniaxial strain. Your comments on bandgap tuning, how the bandgap tuning is in biaxial strain is superior than uniaxial strain?
Yeah, so biaxial strain is a more efficient way of tuning the bandgap of two-dimensional materials. I mean, the easiest way of understanding it is in the case of uniaxial strain. Okay, so you're changing the direction, you're changing the distance of the bonds in one direction, but because of the Poisson effect, you're compressing in the other direction. Okay, and if compression increases the bandgap and tension closes the bandgap, so these two effects, they counteract. Right? Therefore, the strain tunability of the bandgap is smaller. On the other hand, biaxial strain allows you to reach much higher strain tunability. We have these unpublished results that we just, I think we have, we have uploaded to the archive at the end of the year. So in where we have measured the same flake with uniaxial strain and biaxial strain, and you can see how biaxial strain is a more efficient way to apply, to tune the bandgap. Okay. Other question is if the final application makes uniaxial strain easier. That's a completely different question. Then the final application will tell.
Definitely. And one more thing is that in the start of the talk, you mentioned that static strain is complicated, and how about doping in like MOS2 lattice? Doping in MOS2 lattice with a bigger atom like a W. It will create.
Yes, you will. There are already some works on that, but the thing is that those will be interesting for strain engineering, but not for straintronics. For straintronics, you need a strain that can be changed at will by the user. So you cannot put and remove the atoms, real time.
Yes,
so
yes.
you need a way of applying strain that you can change in time. In the same way that you can apply and remove the voltage to the gate in an electric field transistor, in a field effect transistor, you want something similar with the strain.
Thanks a lot. Thanks a lot.
Okay, thank you. So there is now a question by Elsa Prada. So let me unmute you, Elsa. You can ask the question yourself.
Thank you, Ramon. Great talk, Andrés. It's been it's been wonderful, and I've learned a lot. I have a small question. So when you were explaining this Moore law, you mentioned how the length of the channel plays a role, no? So, but then I didn't see very clearly if what matters is the length between the source and drain contacts or the width of the material that you put inside. So it looked to me that what you were talking about was the length between the contacts rather than the width of in this case, of the two-dimensional crystal, or not?
Are you referring to width or thickness?
Well, sorry, thickness. Yes, thickness.
The most important thing is, so for the short channel issues,
yes.
Let's come back to this. There we go.
Yes.
So you start having this problem. So I mean, when you have a long channel, a large distance between drain and source, you have negligible off current. And then the moment this length, this distance is smaller than a threshold value, then you start having more and more current in the off state.
Okay.
And where the thickness comes in this picture like this. This threshold length is proportional to the channel thickness.
Thickness, I see, I see. I was confused. I thought.
So then the thinner, so what you would like, ideally, the ideal transistor will be super long and super thin.
Yes, yes.
Okay? But then semiconductor industry, they want to gain more money. They want to put more transistors in the same chip. So then they make them smaller and smaller.
I see.
And therefore you start having these short channel issues.
Okay. And then my question would be, the next question would be, have you in your Straintronic devices, have you gone to such a short length so that you are testing that this happens with these two-dimensional crystals?
No. Our devices, they're huge if you compare with these short channel issues. Okay. So we fabricate just purely proof of concept devices. They are micro devices more than nano devices. So our channel length, they're typically 10 microns. So we are far from this ultimate limit.
Okay. Very well. Thank you very much.
Okay, there is a question now by Herman Suderov. Let me unmute Herman.
Yeah, thank you. Great talk, Andrés. Thank you. So my question is, maybe I missed that, but maybe you can help me out. So essentially the physics which is behind what you are telling is that you change the atomic positions and then you change the band structure, right? Is this right? So I guess it would be interesting to see if there are correlation effects at some point, although probably not in the materials you mentioned. But my question is more, I mean, what about, because in semiconductors the defects are very important. So you create states inside the gap and these states change completely the behavior. What about these defects in your method? Yeah, so what does, so I mean, these defects in two-dimensional semiconductor materials, what they do
is they typically shift the bands. Okay, so for instance, in molybdenum disulfide, you have a naturally N-type semiconductor, and it's because you have the sulfur vacancies that they dope with the electrons, the material, and also you get Fermi level pinning close to the conduction band. Okay, so that is basically the effect that we see in this kind of materials with these defects. And from the optoelectronic point of view, the presence of defects can play a major role in the mechanism that generates the photocurrent. Because as I discussed briefly, we have a change in photocurrent generation mechanism when we apply compression and when we apply tension. Okay, when we apply tension, we have photogating effect. Photogating effect basically happens when you generate an electron hole pair with light, and the holes, they get trapped in one of these states generated in the middle of the band gap because of defects. So, I mean, of course, defects, they play a major role in semiconducting devices, but sometimes they are actually quite positive, like in the case of photogating effect, right? For example, if that is what you want, right? So sometimes you have to really engineer your defects.
Thank you.
Okay, so there is now a question by Sergio Ulloa. Hello, Sergio.
Hello, thank you.
You can
okay, thank you. I wanted to ask about whether you had actually examined your samples for inhomogeneities in the optical response, because it's sort of connected with the last comment you made that if you have defects or puddles or whatever that are producing photogating in some regions but not others, then you will see an inhomogeneity right on your plane. And I wonder whether you examined that.
Yeah, these strain tunable photodetectors, we used scanning microreflectance and scanning photocurrent in order to monitor local changes in the optical properties. But I have to say that in our case, our spatial resolution is around 1.5 microns. Okay, so we can get these maps with a spatial resolution of around 1 micron. In those maps, they're quite homogeneous. Of course, there are some inhomogeneities, but you don't have like hotspots in some places. Okay, so it's rather homogeneous, which also tells us that the strain is being transferred homogeneously on the layer.
Really homogeneous.
That's important. Yeah.
I mean, the corollary of this is that, of course, when you apply the strain, you change the gap, but you may also change the curvature, masses, mobilities. And so if it is a homogeneous change, can you monitor that, for example? So check mobilities as a function of the strain?
Locally, I'm not sure. With our techniques, I don't think so, but I'm thinking maybe with one of these you know, like near field optical microscopy, maybe will be possible. I could check that. Yeah.
Okay. Well, thank you.
One of the things
very nice talk about.
Yeah, thank you. So one of the things that we really changed as well, apart from the, let's say, intrinsic properties of the material, so we know that we are changing the way the material interacts with traps, okay? Because we are observing this crossover from photoconductive to photogating effect. So we don't know, again, the microscopic mechanism behind it, but we know that this is happening, and it's telling us that for some reason, when we apply compressive strain, the holes, they don't get trapped in these mid-gap states. And when we apply compressive strain, these holes, they get trapped quite efficiently in these traps. So, I mean, apart from the intrinsic things, some of the things are changing also with the strain. So it's quite complex.
Okay, thanks.
Okay, let me see. I see no further questions. So maybe I can ask a question myself. Maybe you mentioned already, but my question is whether you can, using this Straintronics with 2D materials, whether you can explore ranges of the electromagnetic spectrum that you cannot access with the standard semiconductors, like with the standard detectors and things like this.
Eventually, that is the main goal, okay? So, but it's technically quite difficult. So, for instance, in molybdenum disulfide, if you apply 8% of a strain of tension, so you almost close the band gap, okay? So you will pass from a semiconductor that has the absorption edge in the visible to all the way to the deep infrared, okay? So that is the main goal of the project I'm working on. But I mean, that is the ambitious project, okay, the ambitious goal. The thing is that applying 8% of a strain in a device, it is very, very difficult, okay? But eventually it could be done.
Okay, very interesting. So let me see. There are no more questions. Okay, so before thanking Andrés and closing the session, let me mention that next Thursday, we will have another interesting talk by Anna Bomer from Ruhr University in Bochum. And she will be talking about iron-based superconductors, materials, magnetism, and tuning methods. So please come, and we expect you all to attend this seminar next Thursday. And with this, I thank Andrés for the fantastic talk. And I thank you again for attending the seminar series, and see you next Thursday. Okay, bye.
Thank you all. Stay safe.
Bye. Thank you, Andrés.
Bye-bye.